Hello, my name is David Watson, and I'm going to present my paper, Rational Shapley Values, a decision-theoretic approach to explainable AI. The basic problem setting is as follows. We've got some complex machine learning model, maybe a neural network like the one visualized here, that's used in some high-stakes domain, perhaps healthcare or personal finance. And while these models may be very accurate, they're also opaque in the sense that users struggle to understand the reasoning that goes into individual predictions. This is sometimes called the black box problem in AI. So explainable AI, or XAI, has emerged in the last few years as a set of methods to try and tackle this problem. I'm going to focus in particular on two approaches. One is called feature attributions, where the goal is to try and quantify the input of individual features towards some particular prediction, positive or negative. The other is called counterfactuals, where we find one or several points on the opposite side of a decision boundary that are similar or close to the input point in some relevant sense. Now, both these methods have their advantages, but they also have some disadvantages. Feature attribution methods tend to treat explanations as objective deliverables, so they vary only with the target function and training data, not with user inputs like preferences or beliefs. Counterfactuals are more customizable, but their multiplicity creates new sources of confusion and uncertainty. You can get a very diverse coalition of counterfactuals, and then it's unclear what exactly the summary or takeaway message is supposed to be from that. So the proposed method, rational Shapley values, represents a sort of pragmatic synthesis between feature attributions on the one hand and counterfactuals on the other. So we extend the axiomatic guarantees of Shapley values, that's one particular feature attribution method, allowing user beliefs and preferences to guide the search for relevant subspaces. We do this all within an expected utility maximization framework, thence the decision theoretic angle on this proposal. So what does this mean in practice? We'll say that two applicants with identical feature values are denied credit. And let's say counterfactuals identify two minimal perturbations sufficient for recourse. On the one hand, we can either increase education by 1 unit, or we can increase savings by 1 unit. Now, if these two agents have different sets of preferences over these, maybe this agent on the left has already applied to some programs and is looking to go back to school, whereas this user on the right does not want to go back to school, but recently got a new job and is going to be hoping to save a little bit more each month, then preferences alone are going to determine which of these explanations are optimal for these agents. Our basic strategy is to allow users to inform the counterfactual search and then compute Shapley values with respect to these customized inputs. So this is going to let us go beyond simple or objectivist questions like, why did the model make this prediction for this input, and ask more targeted pragmatic questions like, why did the model predict this as opposed to that? Or why did the model predict this as opposed to that given some conditioning set? Or why did this model predict this as opposed to that given some conditioning set and maybe further restrictions on remaining variables? The details are obviously in the paper. I'll just say by way of conclusion that there are advantages to feature attributions and counterfactuals, and the two can be fruitfully synthesized into a single method, incorporating agentive beliefs and preferences in a flexible manner. So rational Shapley values preserve and extend the axiomatic guarantees of classical Shapley values within an expected utility maximization framework. Thank you very much for your time, and I hope to see you at the conference.